Welcome back to the Building Code Pros podcast, your expert resource for navigating the world of building codes. In today's episode, we're taking a closer look at a crucial topic. Let's get started. We are launching a deep dive today into, well, the real bedrock of construction. The 2024 International Residential Code, Chapter 4. It's all about foundations. Now, for builders, this might not seem like the glamorous part, but it is absolutely fundamental, non-negotiable, really, because if the foundation isn't right, nothing above it matters, does it? It's got to handle every single load.
That's exactly right. Chapter 4 basically governs everything from the ground down to, well, the structure that holds the sill plate. Get this part wrong, and you're looking at potential structural issues, serious moisture headaches, maybe even costly future repairs. We're talking stability here, whether you're building near water, using wood foundations, or dealing with, earthquake zones.
Okay, let's dig in, starting right at the ground level. Site prep, soil, drainage, the basics.
Drainage has to be top of mind. Water management is key. The code is pretty insistent on surface grading. It says the ground must slope down at least 6 inches within the first 10 feet away from the foundation. That's a hard rule unless there's some kind of physical barrier, like, say, a property line right up against the house.
Right, I see. And what if you do have that barrier, maybe a tight lot line, a shared driveway? How do you handle drainage then?
Good question. If you've got an impervious surface there, like concrete or asphalt, within that 10-foot zone, it still needs to slope away. But the minimum slope requirement drops a bit, down to 2%. The main idea is simple. Keep water from pooling near the bedding.
Makes total sense. Okay, so water's flowing away. What about the ground itself? Can it actually hold the weight of the house? How do we know?
Right, soil capacity. This is where soil investigation comes in, sometimes. If the soil looks iffy, maybe it seems expansive or really soft or it's clearly shifting, the building official can actually require a geotechnical report. But honestly, a lot of projects just rely on the code's default values.
Okay, so let's say you skip the soil testing, which can be expensive.
Yeah.
What's the code force you to assume? What's the safe bet?
You have to use the conservative bearing capacities listed in the tables. The number most people need to remember is 1,500 pounds per square foot, or PS. That's generally the assumed value for soils like silty clay or mixtures like that.
1,500 PSF.
Yeah.
Got it. And what if you look at the site and you really think the soil's weaker than that?
Then you have to get a proper soils investigation. You can't just, guess or hope for the best. If the soil looks weaker than that 1,500 minimum, that's asking for trouble.
Understood. So what if you do find bad soil, compressible, shifting stuff? What then?
You absolutely cannot use that material as fill under your foundation, period. It either needs to be completely removed down to solid ground or needs to be properly stabilized in place. Using that kind of stuff as fill, it's just setting yourself up for settlement issues later.
Okay, so site prep done, soil assessed. Now we move up to the actual footings, the concrete base. What are the basic rules for size?
Every exterior wall needs support from a continuous, solid footing. Usually concrete, but sometimes masonry, crushed stone, even treated wood in specific cases. Dimension-wise, the minimum width is 12 inches, and the minimum thickness or depth is 6 inches. Those are the baseline numbers.
And I remember there's a specific rule about how far the footing can stick out from the wall it's supporting.
Yes, exactly. It's called projection. It has to project at least 2 inches beyond the wall on each side. But, and this is important, that projection can't be more than the footing's actual thickness. So for a standard 6-inch thick footing, it can't stick out more than 6 inches past the wall.
This is where those prescriptive tables in the code become really helpful, right? Saves doing complex engineering sometimes.
Yeah.
Can you give us an example? Maybe compare two houses on the same soil, same climate, but with different exterior finishes. Show how that changes the footing.
Yeah, that's a great way to see it. It really highlights the impact of dead load. So imagine you've got two projects side by side, both at 2-story houses with basements. Let's say the soil capacity is decent, maybe 2,000 PS, and they're in an area with a 50 PSF snow load. Pretty standard stuff.
Okay, identical conditions. House number 1 is standard light frame construction, maybe vinyl siding, something light.
Right. For that light frame house, you look at Table R 403.1, and it tells you you need a footing that's 15 inches wide and 6 inches thick.
15 by 6, okay. Now, house number 2, same basic structure inside, but the owner wants brick veneer on the outside.
Ah, brick veneer, that adds a lot of weight. It's a significant dead load increase.
So how does that change the footing requirement, just that aesthetic choice?
It bumps the required width up considerably. Instead of 15 inches wide, that footing now needs to be 19 inches wide. Still 6 inches thick, though. That extra 4 inches of width is critical to spread out the heavy load from the brick veneer onto the soil properly.
Wow, 4 inches wider just for the brick. So if a builder just used the 15-inch footing on the brick house,
They'd be seriously undersizing it. That could definitely lead to settlement problems down the road.
well,
It shows how you really have to use those tables correctly.
that really drives the point home. Okay, shifting gears a bit, let's talk about dealing with cold climates and frost lines. Traditionally, you had to dig footings way down deep, below the frost line. Expensive.
Very expensive and time-consuming. But the code now allows for an alternative. The Frost-Protected Shallow Foundation, or FPSF.
FPSF. What's the main advantage there for a builder?
Efficiency, mostly, and cost savings. Instead of digging maybe 4 or 5 feet down, you use insulation strategically. Now, there's a catch. FPSF is generally only allowed for buildings that are consistently heated. The code says the monthly average indoor temp needs to stay above 64 degrees Fahrenheit. You use specific types of rigid insulation, rated to ASTM standards, placed vertically against the foundation and horizontally out from the footing.
So you're basically using insulation to keep the ground under the footing from freezing, right?
Yeah.
How much insulation?
It depends entirely on your local climate. You look up something called the air freezing index for your area. It's a measure of how severe the winter is. That index value, found in table R403.31, tells you the required R value of the insulation and how wide the horizontal insulation needs to extend out from the building. It's a smart way to avoid deep excavation.
Interesting alternative. And speaking of alternatives, I noticed the code allows crushed stone footings in some situations.
Yes.
It seems unusual.
It does, yeah. Crushed stone can be used as a footing base for standard cast-in-place concrete foundation walls, but only in lower seismic zones, specifically seismic design categories A, B, and C. The key here is installation quality. The stone has to be clean, angular, not rounded river rock, and it absolutely must be compacted thoroughly, usually in 8-inch layers or lifts using a mechanical plate vibrator. Get it really dense.
Good to know. Okay, let's move up from the footings to the foundation walls themselves. These walls have to hold back all that earth pressure. What's the basic concrete strength we need?
The standard minimum compressive strength, what we call F'(C), is 2,500 psi for most residential work. However, if you're building in a higher seismic area, specifically categories D0, D1, or D2, that minimum strength requirement bumps up to 3,000 psi. You need that extra bit of strength for earthquake forces.
Makes sense. Now, probably the biggest factor influencing foundation wall design is the unbalanced backfill height. Can you break that down simply?
Sure. Just think of it as the height difference between the soil level outside the wall and the ground level or basement slab level inside the wall. It's the height of soil that's pushing on the wall without an equal force pushing back from the inside. The magic number here is 4 feet, or 48 inches. If your wall is holding back more than 4 feet of unbalanced soil, and it doesn't have something like a floor system bracing it at the top, you generally can't just use the standard prescriptive tables in the code.
So, more than 4 feet of unbalanced fill often means you need an engineered design.
Typically, yes. Or you need to make sure there's permanent lateral support, like properly connecting it to the floor joists above.
This leads to a really critical point about construction safety and sequencing. Bracing before backfilling. What happens if someone just dumps soil against a tall, unbraced foundation wall?
Oh, that's incredibly dangerous. A recipe for disaster, really.
Yeah.
If that wall is designed for 4 feet or more of unbalanced backfill, the code is crystal clear. You must anchor the wall to the floor structure above it, or provide adequate temporary bracing before you start placing backfill against the outside. If you backfill against an unbraced tall wall, the lateral pressure from the soil can literally just push the wall inwards. It can buckle or even collapse completely. Huge safety risk, huge liability.
Yeah, you definitely don't want that happening on your job site. That bracing requirement makes perfect sense then. And this need for lateral resistance is also why the code has such detailed rules about reinforcing steel or rebar in the walls, isn't it?
Precisely. Concrete is strong in compression, but weak in tension. The rebar handles those tensile forces caused by the soil pressure bending the wall inwards. Prescriptively, the code usually requires at least one horizontal number 4 bar near the top of the wall within the top 12 inches. And then for vertical bars, the requirements, the bar size, and how close together they need to be can vary quite a bit. It depends heavily on that unbalanced backfill height and also the type of soil pushing against it. You really have to consult the tables like R404.1.3.2. It gets complex.
It shows these aren't just simple walls, they're retaining structures. Okay, walls up, concrete secured. Now we need to connect the wood framing above it. Anchorage. What are the basics?
Right, connecting the wood sill plate to the concrete. You need anchor bolts, minimum half-inch diameter. Spacing is typically no more than 6 feet apart along the plate, and they need to be embedded deep enough, at least 7 inches into the concrete or into the grout if it's a masonry wall.
6 feet on center, 7 inches deep. Standard stuff. But I bet that changes in earthquake country, too.
Absolutely. In those higher seismic design categories D0, D1, and D2, the requirements get tougher. For houses over 2 stories tall in those zones, the maximum spacing between anchor bolts drops from 6 feet down to 4 feet. And critically, you also have to use special plate washers, usually 3-inch by 3-inch square steel washers, under the nut on the anchor bolts along any braced wall lines.
Plate washers. Why the bigger washers?
During an earthquake, there's a lot of uplift and side-to-side force trying to rip the sill plate off the foundation. That big plate washer helps spread that load out over a larger area of the wood plate, preventing the bolt head or the standard round washer from just pulling right through the wood. It keeps the house tied down better.
Keeps the house tied down. Got it. Okay, for our last section, let's talk moisture. Managing water around the foundation and also dealing with the space underneath the floor, the crawl space.
Right. Water management again. Foundation drains, like perforated pipe or gravel drains, are generally required around any foundation that holds back earth and encloses usable space below grade, like a basement or crawl space. These drains should be installed down at the footing level or even slightly below the top of the footing to collect water before it builds up pressure against the wall. The main exception is if you happen to be building on really well-draining soil, what the code calls Group 1 soils, which is basically clean sand and gravel.
Yeah.
Then you might not need the drains.
Okay, drains handle the bulk water. What about just dampness from the soil? The code talks about damp-proofing versus waterproofing. What's the difference, and when is each required?
Good distinction. Damp-proofing is the standard baseline requirement for most foundation walls enclosing interior space below grade. It's typically a coating, like a bituminous or asphalt-based material, applied from the finished ground level down to the top of the footing. If it's a masonry wall, you usually need to put a thin coat of cement plaster, called parging, on first. Waterproofing, on the other hand, is a much more robust system. Think thicker membranes, like rubberized asphalt or specialized sheet membranes. Waterproofing is only required when you have a high water table or you know you're dealing with severe soil water conditions where actual hydrostatic pressure, liquid water pressure, is expected against the wall.
So damp-proofing stops vapor and minor dampness. Waterproofing stops liquid water under pressure.
That's a good way to put it, yeah.
All right, last piece, under the floor. Crawl spaces. Builders seem to handle these in 2 main ways now, vented or unvented. Let's start with the traditional vented crawl space.
Okay, the classic vented crawl space needs openings to the outside. The standard rule is 1 square foot of net-free vent area for every 150 square feet of crawl space floor area. The idea is to let outside air circulate and hopefully dry out any moisture. However, there's a big exception. If you install a proper vapor barrier, what the code calls a Class 1 vapor retarder, basically thick plastic sheeting covering the entire ground surface in the crawl space.
Like 6mm poly.
Exactly, like 6mm poly, properly lapped and sealed. If you do that, you can drastically reduce the amount of required vent area, down to 1 square foot of venting for every 1,500 square feet of floor area, plus you need at least 1 vent near each corner.
So putting down the plastic means way fewer vents, which probably helps with energy loss too.
It does. It minimizes bringing in potentially humid outside air in the summer or cold air in the winter.
What about the other approach? The unvented or conditioned crawl space. This seems more popular now for high-performance homes?
It definitely is. With an unvented crawl space, you essentially treat it as part of the conditioned volume of the house. First step is, again, that Class 1 vapor retarder fully covering the ground, sealed at all laps and edges, and often run up the walls a short distance. But then, instead of vents to the outside, you need to actively manage the air inside the crawl space. The code gives you a few options. You can supply a small amount of conditioned air from your HVAC system, or you can install a dedicated exhaust fan, or you can use a dehumidifier sized for the space. The goal is to keep the humidity low and the air quality good.
So seal it tight and then mechanically control the moisture.
That's the essence of it.
And one last practical detail, getting into these spaces for repairs or inspection.
Yeah.
What are the access opening size requirements?
Yeah, you need to be able to get in there. Access is required to all underfloor spaces. If the access opening is through the floor above, it needs to be at least 18 inches by 24 inches. If the access is through an opening in the perimeter foundation wall, the minimum size is slightly different, 16 inches high by 24 inches wide.
Good details to remember. Okay, this has been a fantastic deep dive into Chapter 4. Before we wrap, let's boil it down. What are the absolute Must remember takeaways for our listeners.
All right, 4 key things. First, soil and grading dictate everything. Don't guess on soil strength, assume 1,500 PSF minimum if untested, and always ensure that proper 6-inch drop in 10 feet for surface drainage away from the house. Water is the enemy.
Okay, number 1, soil and drainage. What's second?
Second, footing sizing is load specific. Use those prescriptive tables carefully. Remember our brick veneer example, adding weight means adding footing width. Don't use a generic size, match it to the actual loads of your specific structure.
Right, load-specific footings. Number 3.
Third, and this one's huge for safety, 4 feet of backfill is the trigger for lateral bracing. If that foundation wall holds back 4 feet or more of unbalanced soil, it absolutely must be braced by the floor system or temporary supports before you backfill. No exceptions, prevents wall failure.
Crucial point, bracing before backfilling over 4 feet. And the final takeaway.
Finally, master crawl space moisture control. You have 2 main paths. Vented or unvented conditioned. Choose one strategy and do it right. Either vent properly, maybe using the reduced venting with a ground vapor barrier, or fully seal it and actively condition or dehumidify the space. Don't do it halfway.
Excellent summary. Soil, footing loads, bracing, and crawl space control.
Got it. And maybe just one last thought to leave with folks. Think about that frost-protected shallow foundation. Right now, it's mostly seen as a cold climate solution to avoid deep digging. But considering the energy benefits of having insulation around the foundation edge, could we see FPSF principles become more common everywhere, even where frost isn't deep, just for better thermal performance of the whole building? Something to consider.
Interesting thought. Using insulation for energy efficiency, not just frost protection. Food for thought, indeed. And that's our breakdown for today. We hope this gives you a clearer understanding of the topic. For more articles and resources, be sure to visit buildingcodepros.com. Join us next time for another episode.
Thanks for listening.